Okay, this particular lecture for our Capstone design course is going to focus on building systems. We have several different lecture outcomes that we're going to try and achieve today. First of all, defining the term load path. I suspect you've heard the term before. We're going to get a pretty specific explanation of what it is and how the codes actually reflect the need for a load path. Then we're going to move on to identify and explain the details of 4 different types of common building systems for concrete and masonry structures. This will not cover every type of building system possible, but again, focusing back on concrete and masonry, which are the prevalent structural materials used on the site. We're going to talk briefly about shear walls. Rather than getting into the specific design details of shear walls, we're going to focus on common considerations relative to layout of shear walls. And finally, we'll try and identify for you what considerations, or at least get you started thinking about what considerations you're going to need to look at in determining what the right building system for your particular structure is going to be. So in this lecture, we are not going to talk in any way, shape, or form about designing particular elements such as beams or columns or walls, but more looking at how we can take the entire structural system as a whole and identify where the load is going from top to bottom. We'll start by defining the term load path, and rather than trying to come up with our own definition, we're going to go right to the IBC. And if we look at the IBC section 1604.4, this is a direct quote, and we'll go ahead and read it here. Any system or method of construction to be used shall be based on a rational analysis in accordance with well-established principles of mechanics. Such analysis shall result in a system, and here's the critical part, that provides, quote, a complete load path capable of transferring loads from their point of origin to the load-resisting elements. So we're basically looking at different types of loads, of course, starting at different locations. If I consider a generic building, say here, in the United States, sitting here in the Shear building, for example, if I take a snow load on the roof, the question is, how does that snow load get transferred from the roof eventually down to the ground? If I take a live load or a dead load in a classroom, how does that load get transferred? Does it need to go through beams or columns or walls? What exactly is our mechanism? So that's what we're going to look at. Now, in terms of a load path, there are actually, with respect to that question, going to be several different considerations that as a structural engineer you're going to consider in any given structure. The first and clearly the most important thing in any load path is the idea that we have to satisfy the principles of mechanics. So we started structural engineers way back in statics and dynamics and mechanics of solids, and we learn all these principles. We have to make sure that there actually is a load path. So satisfying the principles of mechanics really is just to check that we actually do have a load path. Not necessarily that we've got the best load path or alternative load paths or anything else, but simply making sure that there is a satisfactory load path that works based on the principles of mechanics. Then we have other factors which really help to dictate what is the best particular load path for a certain system. Architectural plan. If I'm designing a large ballroom in a casino structure, the architect may prohibit me, for obvious reasons, from putting a massive column right in the middle of that ballroom. So we need to consider what the architectural plan and the functionality of the building is going to be. Obviously, economy. We want to try and do it in an efficient way that doesn't waste our resources and our financial considerations. And then finally, constructability. All 3 of those being very important for different reasons. Constructability basically reflecting the fact that it can't just be a paper design. We have to actually implement it in the field. With respect to a load path, we're really going to break it down for the rest of this lecture into 2 different types of loads that we have to deal with in any given structure. And if I just take a basic frame structure and consider a frame structure such as this, I'm going to have gravity loads. Those might be the loads acting in this particular fashion, dead loads, snow loads, etc. And I'm also going to have lateral loads, and maybe those come from wind. Maybe they come from earthquake forces. So I have to have essentially a load path that works for both of those types of loads. We're going to break this up then into 2 different force-resisting systems, and we'll use the kind of acronym here FRS for a force resisting system, which will give us the vertical force resisting system and then the lateral force resisting system. These will be different systems. They will obviously have to work together in the entire structure, but we'll separate these two out as far as the discussion goes. So again, these can be either completely separate or work together, but eventually they have to be constructed as part of a single unit. So let's start with the vertical force resisting system. Easy for us to address because we think of several different types of systems, but basic loads that we're going to deal with are going to be supported by things such as the roof, floors or slabs, beams, girders, columns, walls, footings, etc. Depending on the complexity of the structure, how tall it is, how wide it is, what the spans are, what the material that we're using is, whether it's steel or concrete or masonry, we're going to wind up with different types of structural systems. But these elements that build in to the structural system are going to be the elements that, of course, we eventually have to design. If I look at the lateral force resisting system, this is going to basically, again, have several different types of systems that are possible. And if I consider the elements that might be part of a lateral resisting system, you're going to see we again have the roof, the floors, the slabs, the beams, girders, columns, walls, footings. So it's a very similar list, if not identical, basically to make the statement that these elements are going to need to resist two different types of loads. Now, I can design a system, as we'll talk about here, where the walls may resist both gravity loads, or that is vertical loads, and lateral loads. Or I can design a wall that resists only lateral loads. Or I can design a wall that only resists vertical loads. I just have to work through what that total system is going to be. Okay? The other thing we have to remember when we talk about lateral loads is that if I take a floor plan and look at this simple plan view of my structure, I have to consider two different directions. That is, what happens when the wind blows that way and what happens when the wind blows that way. And if I want to look at subsets of that, I can look at whether the wind on the page here is blowing right to left or left to right, what happens at a 45-degree angle, etc. But I can break it up into two different systems at the very least. So I have to consider directionality with respect to the lateral force resisting system as well. All right, if we talk about, again, a simple example here to kind of put some meat to this, we're going to look at an element that can be part of both a vertical force resisting system and a lateral force resisting system. And what I'm going to use is a wall. Okay, so we'll just imagine a solid block or brick wall in a typical building structure. And depending upon how I decide to set up my load path, I can have that wall potentially being what we would call a bearing wall. And in a bearing wall system, I'm going to have gravity loads acting on the top of the wall. Maybe it's supporting a roof, or maybe it's supporting a floor. Depending upon what the structural layout is, I might have either or both of those. But the load will act on the top of the wall, and then through axial compression in the wall, it'll be transferred down to the base. That's what we call a simple or bearing wall. I can also look at what we call a curtain wall. And in a curtain wall system, I'm going to basically have the wall carrying lateral loads that are perpendicular to the plane of the wall. So if I think about wind pressure acting on this particular wall, we can see the arrows on the screen. That would be an example of a curtain wall system. And of course, just about every building structure has some form of this, whether it's brick or block or drywall, sheathing, etc. Finally, I have a shear wall. And a shear wall is going to resist loads that are basically lateral, but in the plane of the wall. So if I consider how this wall is going to act, it's going to be a very stiff wall, resisting bending in the plane of the wall. Rather than bending out of the page, it's going to bend within the plane of the page as it's drawn here. So I have three different types of setups here, depending upon what the system that I have in this particular case is going to be. What I have for the vertical and lateral force resisting systems, I may have to design this wall essentially to be either a bearing wall or a curtain wall or a shear wall, or I could have some combination thereof. So it's very conceivable that I'd have to design this wall to handle all three types of loads here. That is in-plane lateral, out-of-plane lateral, and vertical loads. So depending upon the structural system that we choose, there are going to be several different possibilities. Before we get to those different common building systems, I want to just briefly mention the importance of connections. If I design beams and columns, foundations, slabs, all of these things have to be designed properly to resist the loads that are going to be applied to them. But the connections between those elements are a key point of the load path. If I have a good beam design and a good column design but no way to connect the two, then there's not going to be any way of transferring the load from the beam to the column. This is extremely important in high seismic situations, and there is a separate lecture that Dr. Deinhardt has prepared for you on seismic design. I know he has some real good slides of what happens when you have some bad designs here in terms of the connections. You do wind up with, unfortunately, your building collapsing on you simply because of bad connection design, regardless of how good your beams and columns and slabs may be. So because of this, if you look at the International Building Code, just for reference, there are going to be, for example, several special provisions related to connections. The key point to make here is that those connections are, very simply, very big, a very important part of our load path. Okay? We don't design them in the simplistic ways that we have talked about for beams and columns and such. All right. I want to go now to talk about 4 different common systems that we can have for concrete and masonry structures. And we've got a very simple graphic here, a schematic that we're going to use. We have a bearing wall system, a moment-resisting frame, a building frame system, and a dual system. And what I'd like to do is briefly go through each one of these. We're going to start with what happens for a bearing wall system. So if you look at the graphic on the upper left, a bearing wall system, we can see here we have essentially what looks like a wall. And in that wall we have both lateral loads and gravity loads applied. Now, the bearing wall system in this terminology is simply a common term for this type of system. We talked about what a bearing wall is before, but when we talk about a bearing wall system, we are actually going to talk about the following. Vertical loads are resisted entirely by the bearing walls. That's self-evident. That's what we just said. The loads are going to be transmitted to the bearing walls, through the roofs, to the floor slabs, etc. If I need beams to reduce the spans in the floor slab, provide intermediate support, I can do that. But what's interesting is the terminology that's commonly used, bearing wall system, also implies that the lateral loads are going to be resisted by those bearing walls. Those bearing walls will act as shear walls, just changing the terminology. It's the same wall in essence, but it's going to act as a shear wall to resist loads in the plane of those particular walls. So a simple box type structure is what we're talking about here. This is common actually across the United States in situations where I have large masonry structures. Okay, so if I think about masonry, most masonry structures are going to be bearing wall type systems because I don't necessarily have any frame support. I don't have a bunch of columns and beams and that type of thing. Okay. Second system we're going to talk about, you can see a very similar schematic here to what we just looked at, but completely different at the same time, is a moment resisting frame. If I look at the similarities are that I have a single system resisting both gravity and lateral loads. The difference is I'm now using a frame instead of a wall. So if I look at a moment resisting frame, the vertical loads in this case are going to be resisted by a space frame. If I think about a steel building under construction, so you can see the grid of steel, the three-dimensional grid of steel, very common situation. That is going to basically be when you have your floor slabs, it's going to form your vertical resisting system. The load will be transferred from the live load or the dead load to the floor slab, from the floor slab out to beams, from the beams to the columns, from the columns down to the foundations. That's kind of self-evident. If I think about lateral loads, what I in essence have is a frame system with moment connections or rigid connections to resist lateral loads. And if you think back to structural analysis, the easiest way to look at this is to take this type of situation where I give you a frame, and instead of just putting vertical loads on it, let's also put lateral loads on it. And what happens is the beams and columns deform as an overall unit. The structure behaves, it deflects to the left or to the right, depending on which way the force is acting. The members deform based on the applied loads in the gravity fashion. So I wind up with a single system where I have designed it to resist both the gravity and lateral loads. Again, I have to have, in general, rigid beam column joints. So if I consider this joint right here, that's going to be a rigid joint rather than simple pin connections, because I need the moment resistance to have some stiffness. The loads are going to be transmitted to the space frame typically by curtain walls. I might have a brick facing on this as a simple system. So in each of these two cases, the bearing wall, the bearing wall system and the moment resisting frame, I've got a single type of structure that resists both gravity and lateral loads. When we go to what we call the building frame system, and again, this is just the common terminology, a building frame system is going to use a wall to resist, as we can see from the schematic, lateral loads, and it's going to use a frame to resist gravity loads. So when I consider that and piece it together, what we have is the following. Vertical loads are resisted by a space frame. I have beams, girders, columns, floor slabs, same basic concept. But my lateral loads are going to be resisted entirely by walls. Now, because those walls are only going to be designed to resist lateral loads, we're now going to go ahead and call them shear walls. So a shear wall, again, is a wall where I basically have the wall and the in-plane lateral load being resisted by that wall. It's essentially a cantilever beam if you want to take the drawing that we have here and turn it on its side. The lateral loads are resisted entirely by those shear walls. And we get these shear walls to resist the lateral loads by having forces transferred throughout the entire structure to those shear walls, those points of resistance. Those are done by diaphragms. So if I consider a floor slab, and we'll talk about shear wall layout in a little bit, if I consider a floor slab, the floor slab acts to distribute the loads. I can basically take the floor slab, I might have a shear wall on each side, and I can count on the floor slab making that structure act as a unit. It's what we call diaphragm action. The last system is very, very similar to the one I just mentioned. It's a dual system. The difference between a dual system and a building frame system is that the vertical loads are going to be resisted by both the space frame and the bearing walls, and the lateral loads are also going to be resisted by both. So rather than simply saying in the building frame system, we have the concept that the frame is going to resist the gravity loads and the shear wall will resist the lateral loads. I'm going to design it as a dual system, letting each of those two elements both resist vertical and lateral loads. If I consider how to design something like that, it gets really complex, because if I consider, for example, the lateral load, if I have a shear wall and a moment frame, how much of the lateral load? Let's say I have a lateral load of 10 kips. Let's say it's due to wind. How do I get that 10 kips distributed? Is it going to be resisted half by the shear walls and half by the moment frame? Or is it 1/4 by the shear walls and 3/4 by the moment frame? Or and on and on and on with other possibilities. How do I determine that? It's complicated, but you would use a stiffness approach. That is, consider the stiffness of each of those load-resisting elements, and the stiffer the system, the larger portion of load it typically carries. Just as if I had two springs side by side with different stiffnesses, the stiffer spring would handle a larger portion of the load. So when I get into these dual systems, it becomes a much more difficult system, again, to analyze and design. So the key to what we want to do here is look at what do we do with your structure, okay? What type of system are you going to use for your structure in Honduras? Well, what are the considerations that we want to look at? Okay, let's just kind of consider what are some of the things that are going to affect your choice. And think about what we started with at the beginning of the lecture. I'm not going to answer all the questions here. We're just going to kind of pose them. This is where your work really comes in. But think about the first couple of slides. We talked about aesthetics, economy, constructability, those sorts of facets. The question here is, what are the specific elements for your particular structure that dictate it? Previously, I used the example of a ballroom. Well, you're not designing a ballroom, but you're designing maybe a computer lab or a classroom or other types of structures for the Amigos site. So what are you going to need to do in terms of satisfying those types of architectural and economic and constructability requirements? Again, we have to have something that works. That's the number one goal, is we have to satisfy mechanics. And ultimately what this boils down to as a designer is, once we've established this system, the question then becomes, what loads are each of your structural elements going to need to be designed for? So once I've established the structural system, now I have dictated what the load path is going to be, and I have to decide what the columns are going to handle, what are the beams going to handle, each particular beam, that is. What are the walls going to be designed for? Gravity loads, lateral loads, both, the roof, etc. So it's after I decide on a system that I move on to designing the different individual elements. Of course, I have to come up with the actual load magnitudes as part of that overall design process as well. Well, I gave you 4 different systems, and we have had a couple of different lectures available to you on typical construction practices, a whole lot on the history on the site. So we can actually boil it down for you to 2 basic choices for your structure. And we're going to give you 2 choices on the basis of what is realistic to be done on the site. We know we're going to be using some form of masonry and some form of concrete construction. So we're going to allow essentially one of 2 systems to be chosen, either a bearing wall system or a building frame system. What we've eliminated is essentially a dual system, which is a very complex system, and we've also eliminated a moment frame. We're not going to be designing structures where you're just going to have nothing but beams and columns. We know there's going to be masonry involved, so what we're doing is essentially taking that masonry and utilizing it in these 2 systems. A dual system, as I said, is far more complicated to understand or to figure out what proportioning I do. So it's going to be a building frame system if you decide to use your beams and columns, and a simple bearing wall system if we decide not to. Now, the choice is going to be different for every structure. So we're talking to a couple of different groups here, different years. It's going to be different for every unique structure. We have to look at the architectural requirements for your particular structure that you were given in the first couple of class periods. Okay? If we just kind of back again to some specific considerations relative to the Amigos type projects in choosing the system. One thing to note is, again, we're going to use a shear wall for either type of system. Okay, so what we have to do is actually identify some things such as, where are potential shear wall locations? Okay, I've already said that you're going to use one of 2 systems, both use a shear wall or multiple shear walls. So we have to make sure there are locations within our walls that can act as shear walls. If it's going to be a shear wall, it's basically going to be a solid wall, as we'll mention or a relatively solid wall, as we'll mention in a little bit. What are your wall locations in general? Start with that question. Obviously, you're not going to add a shear wall. You want to try and work it into the architectural requirements that are existing for you. If we need to modify the architectural requirements, you can ask special dispensation from Dr. Deinhardt and myself. We'll pass it down to the clients if you need to. And that typically comes from the 4th question that I've posed here. What happens with windows and doors? If we have nothing but windows around the entire perimeter of the structure, it's hard to come up with a shear wall that's a relatively solid wall to resist those lateral forces. So we are going to need to talk about where shear walls can be put in, or you're going to need to look at first where those shear walls can be put in your particular structure. We're going to talk about designing masonry shear walls throughout the rest of the semester here, and you need to make sure you've got an adequate space to handle the loads that you come up with from your lateral force calculations and potentially your gravity calculations. Bottom line is, openings make it tougher to design shear walls, to design walls in general, but specifically shear walls. So as I've said, we want to wind up with solid walls as shear walls. Now, we'll talk a lot more about how to design a shear wall later, but at this point in time, because what you're trying to do is identify a load path, we have to talk about a shear wall layout in general terms. Again, we're going to start with a generic structure. Okay? General concepts. You need shear walls in both directions. We said the lateral loads are going to be in two different directions. We don't know whether the wind is going to blow from the east or the west, or whether it's going to come from the north or the south. So we have to have lateral systems that work in both of those two planes. That means we need shear walls in each direction. The shear walls should, if possible, be symmetrically located. That provides an even or well-distributed resistance. And if possible, we want to use more than one shear wall. These are kind of very similar in terms of the requirements. Now, what we want to do here is go through a very, very simple, the most simple building that we can. Let's say that that's our structural layout. It's a simple rectangular shape. You can imagine, pick some numbers. Let's say, for sake of argument, it's a 40-foot by 70-foot building or something of that nature. Doesn't really matter, but we're looking at it in plan. A typical shear wall layout could, this is one option, could look like that. So if you want to think now about what we've done here on this simple design, I have added a shear wall in each direction at each corner. So I've actually added a total of 8 shear walls. If the wind blows in this direction, what I'm going to have is that shear wall and that shear wall and that shear wall and that shear wall are going to act together to resist my forces. If the wind blows from the left or the right, or the earthquake shakes the ground such that it accelerates in those directions, then the other 4 shear walls will act to resist the loads. If I want to think about what this structure basically looks like, the easiest thing to imagine is simply taking a cardboard box. If you take a cardboard box and you stiffen up the corners of that box, say by adding some simple little metal angles or something like that, what I'm going to wind up with in plan is something that looks like this. So I'm stiffening up the corners to take the resistance. I'm also doing it in a symmetric fashion. If I only put my shear walls on this particular plan on the left side, if the shear walls are only over here, then I'm not going to have much resistance on the right side, and unless I can funnel all of the lateral load to the left side, I have a very poor resistance for that structure. So other typical layout, or other possible layouts, I should say, could look like this. This is very similar, except I've, in the left-right or east-west direction on the screen, I've changed from having the corner shear walls to a longer shear wall in the center on each side. Maybe what I have is a nice big space there where I have a solid wall. Okay? Depends on what the architectural requirements look like. Here's another option. If I look at this case, I've moved them from the outer walls to the inner sections of the building. And again, if the building's large enough and I was going to put walls there, maybe I can make use of those. What happens oftentimes in skyscrapers is really a variation on this theme, where I have elevator shafts make good shear wall locations, often at the core of your building. So the bottom line is there are a lot of options, and you have to look at your particular structure, see what the architectural requirements are, and try to meet those as much as we can, such that we don't have to change the details that are given to you. Also realize that in just about every project, there's going to be a give and take between the architect and the engineer and or the contractor. So it is not unusual for you to say, hey, I really can't find a good shear wall location here. Can I propose that maybe we work around this by shortening this window or adding in something here? So those kinds of give and takes are possible, or gives and takes are possible. You need to look at it, again, in the context of your particular structure. If we move on to some considerations for your vertical force resisting systems, we know you're going to use a shear wall, or rather at least several shear walls, hopefully, in your lateral resisting systems. For your vertical force resisting systems, some of the considerations are going to be more based on things like potential column locations. Okay, the ballroom example of not putting a column in the middle of the ballroom to resist vertical loads. So what do I need? I need some large-scale horizontal beams or girders to transfer the load out to the existing column locations. If I need to add columns, that's another common situation where you wind up dealing with architects a lot, is the need to add or increase the sizes of columns in terms of what they suggested on your particular structure. I need to look at potential wall locations. If I'm using a bearing wall system, obviously the bearing walls have to be satisfactory enough in terms of being solid enough that they can handle the loads that are required to be handled. You can make some assumptions regarding the construction on site. You can assume that all the walls are in fact going to be masonry, that is in particular masonry block or CMU, concrete masonry unit, to use the proper term. You need to look at where the wall or where the window and door openings are suggested to be in your particular architectural drawings. Okay. Again, we said already that it's hard to work with shear walls where there are large windows and doors and openings. Also for bearing walls, perhaps less to that extent, but we still need to make sure that we satisfy the rigidity requirements by providing solid enough walls. A couple of pictures are probably the easiest way from the site to kind of look at this, and I'm going to go back to the chapel and guest house, which was constructed from 2001 to 2003. And this was actually a split-level structure. So if you look, we basically got a floor down here, a floor down a little bit lower. It's a little bit harder to see on this angle, and then an elevated floor up here. First thing to comment on is avoiding split levels. They become very, very difficult and muddy to analyze. But for purposes of looking through here, there are some real good details that we can look at from this particular picture by looking at different elements. If I look at the corner here, as an example, it would have been very difficult to design this wall as a bearing wall. It's basically a large window opening. So if I'm trying to take the loads above, I've got right in here, at this level, I've got a solid concrete floor, about 4 or 5 inches thick, supporting the chapel above. Well, if I try and take that load down to that wall is not going to work as a bearing wall very well because I've got a large window opening. So this structure, because of that, was designed using a building frame system. What we did is we did find some locations for shear walls, but we used a frame system to handle the load path for gravity loads. So if I look at the load from the wall comes down, the load from the chapel. The load from the chapel comes down, and it's basically distributed out to this particular beam. So we're using, rather than a wall, we're using a beam to transfer the loads out to a column over here and a column over there, which then take the load down to the foundation. So this is an example where the choice became fairly easy because of the architectural requirements with those large windows. If I look at this particular wall, this is the wall that kind of separates the two sides of the chapel, or of the chapel and guest house. So I have a residence to the right. Up here is the floor again, and the chapel is over here to the left. That wall very easily could be designed as a bearing wall. Okay, so in this case, should I decide that the load path is such that those are going to be my primary walls, that wall could easily be designed as a bearing wall. Now, it happened in this case that the layout of the, that is the size and aspect ratio of the structure dictated that we wanted to take the load out to that first wall that I showed you in the previous slide, and that's why a building frame system became the only realistic choice. Another thing to point out, just related to the typical way of designing or of constructing things on site, even if a structural beam is not specified, they are going to pour a beam at the top of each wall. That's part of their typical process. Some of it's architectural, and some of it's just a practical way of kind of topping off the wall and then allowing them to connect to the roof. So you will see a lot of what we call a double beam type system, where I might have right over the window a beam at this level here, and then another beam a little bit higher. In this case, it's up about here, where that beam will look like. And then, of course, my columns coming down here and there. And you'll see that in many of the typical photos from the site, as well as probably in your architectural drawings. It's a pretty typical way of doing things on the site. So if there's going to be a beam there, the point is it offers a potential load path. Doesn't mean we have to use it. Maybe it's not going to be a structural beam. Maybe I'm not going to take the load to that beam. But if I decide I want to, I have that option available to me at least. We'll wind up the lecture here with a simple example of what type of work you're going to need to do in the context of these structures. And this is going back to the classroom design for the school complex. I think it was 2005 or so that we worked on this structure. But here you have a simple, what is in essence an architectural drawing, rough architectural drawing, but an architectural drawing nonetheless. And in this case, we went through all of the same questions that we've kind of posed here. In this decision, in this case, it was decided, let's go ahead and ignore the walls as structural elements. There are masonry walls there. They have brick facing, but there's a lot of windows, and so let's just idealize that system for gravity loads as that type of frame. So even though the walls are there, they are not going to be part of our dictated load path as designers. Does that mean that the walls will not resist any load? Not at all. The walls will almost certainly pick up some of the load. But what we're doing is actually providing more resistance than is actually necessary then, because if I happen to remove those walls, or I didn't build the walls correctly, or if I didn't have the walls tied into the rest of the structure, I'm not going to have a lost or a broken load path. I'm still going to have a path through this system that allows me to take the loads down to the foundations. If I look at that system, and again, we're not going to answer the questions here. The questions are for you to answer, but they're for us to pose. What is the load path for the vertical loads here? Okay, this is a fairly obvious scenario, but keep in mind this is a two-dimensional frame within a three-dimensional structure. So I'm going to have to probably have some slabs or maybe a roof or some beams that transfer load out to this particular frame. I do need to consider things like where does the roof connect to your frame? Big difference in terms of the load path if the roof connects right there versus if the roof connects directly over a column. If the roof connects directly over a column, it's not going to apply any load to the beams. If it applies load to the beams, let's call these case 1 and case 2. In case 1, there's really no load from the roof going into the beams. In case 2, I have to design this beam to handle, or that segment of the continuous beam to handle the load which ultimately gets transferred out to these two columns. So I have to consider things such as, again, the framing plan, whether it's a one or two or three-story structure. What about horizontal loads? In this case, again, if I take a system and look at it as a frame, again, it's actually a three-dimensional system, and what I'm actually going to have is some kind of a diaphragm, like that drawn here. It could be a solid slab if you have a multi-story structure, or it could be your roof, but some way of transferring the loads out to the frame on the two sides of the building, or if I have intermediate frames. So I have the lateral load here, and it's going to get transferred through that diaphragm to the frame if I use a moment frame. But we know we're talking, based on our previous statements, that you're going to use a shear wall. So the question is, where is the shear wall, and how big does the shear wall have to be in this particular case? So the bottom line, again, is that we have to answer the question, what types of load does each element need to be designed for? If I pick one little element out of that, here's a column. I could have you do the exercise, focus on that interior column, and it posed the question to you, list the loads that that column has to be designed for. For example, I've got the self-weight of the column, which is clearly a simple axial load. Maybe I have the roof, potentially an uplift force. It's also possible that I have some floor load. If I've got a floor system here with a slab where the load comes in from the beams, and on and on and on. So again, the exercise for you in each individual element is going to be to figure out what loads you have to design for based on what your structural system looks like. So to recap, you need to choose your structural system. You have two options. You either have the bearing wall system or the building frame system. You're going to need to find some shear wall locations that make sense. Granted, you don't have the shear wall designs. You don't know exactly how big they need to be. That's fine. Make some guesstimates. Ask some questions and we can guide you through that process, but look at least for the obvious locations to put shear walls, and then start looking at which individual elements are going to have to handle which different types of load, so that we can proceed, once you have the magnitudes of those loads, to design those elements. So if you have questions, please check in with us. Hopefully this has been some help to you, and we'll see you for the next lecture.